Classification of elements into S, P, D and F blocks. Classification of elements into S, P, D and F blocks. Basing on the orbital in which the last electron of an atom, that is the differentiating electron of an atom, will enter, the elements of the periodic table are classified into 4 blocks. They are S block elements, P block elements, D block elements and F block elements. S block elements, P block elements, D block elements and F block elements. This classification is mainly based on the orbital in which the differentiating electron, that is the last electron of an atom, will enter. We know that in the periodic table we have 18 vertical columns. The first 2 vertical columns we named it as group 1 and group 2 or 1A and 1B in CIS system. In the first 2 groups we have 2 vertical columns. This is the first 2 groups. These are the first two groups. 4, 5, 6. Here in the first group, or in CIS system it is designated as first A group, we have hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. These elements are said to be first A group elements. Here in hydrogen we have only 1 electron, so its electronic configuration is 1s1. Whereas in helium we have 3 electrons, so its electronic configuration is helium, that is 1s2 and 2s1. And in sodium it is neon, 3s1. For potassium it is argon, 4s1. For rubidium it is krypton, 3d10, 5s1. For rubidium for cesium it is xenon, 4d10, 6s1. And for francium it is radon, 4f14, 5d10 and 7s1. That means in almost all these elements the last electron will enter as s1 electron. The last electron will enter as s1 electron. Whereas in the second row we have beryllium, magnesium, calcium, strontium, barium and radium. Here the electronic configuration is s2, that is in beryllium it is 2s2, magnesium it is 3s2, calcium it is 4s2 and rubidium it is 5s2, barium it is 6s2 and radium it is 7s2. That means electron here enter as a s2 electron. Prior to these elements we have inert gas. So these S block elements, the first A group elements, by losing of 1 electron they will get the nearest inert gas configuration. Similarly, the second A group elements or second group elements, they get nearest inert gas configuration by losing of 2 electrons. That's why these elements are claimed as powerful reducing agents. These elements are claimed as powerful reducing agents. They are perfect metals. They are powerful reducing agents and they are also perfect metals. These elements, that is the first A group elements, forms stable compounds with +1 oxidation state, and its second A group elements will form stable compounds with +2 oxidation state. These are the special characteristic properties of S block elements. S block elements, the elements in which the last electron will enter into S orbital are said to be S block elements. In the periodic table, we have these elements in two groups, namely first A group and second A group in CAS system, and first group and second group in IUPAC system. All these elements, that is the first A group elements, by losing one electron, and second A group elements by losing two electrons, will get stable inert gas configuration. That's why they are in a position to form stable compounds in +1 and +2 oxidation states. The tendency of an atom losing electron is said to be oxidation. These elements, they themselves oxidizes. That means they reduce other substances. They supply electrons to other substances. That's why they are said to be powerful reducing agents. They are powerful reducing agents, except hydrogen and beryllium. Almost all these elements are considered as active metals. They are active metals and always form ionic bonds. Now, let us discuss about p block elements. In the periodic table, the last 16 vertical columns in IUPAC system, we named them as 13th, 14th, 15th, 16th, 17th and 18th groups. And in CIS system, they are designated as 3rd A, 4th A, 5th A, 6th A, 7th A and 0 group elements. In these elements, the last electron will enter in p orbital. So they are said to be p block elements. These elements are named as p block because the differentiating electron in these atoms will enter in p orbital. That's why they are called as p block elements. Let us observe these elements. This is 13th group, 14th group, 15th group, 16th group, 17th group and 18th group. In CA system, the same group, they are designated as 3rd A, 4th A, 5th A, 6th A, 7th A and 0 group. Don't get confused. 13th group is called as 3rd A, 14th group is called as 4th A, 15th group is called as 5th A, 16th group is called as 6th A, 17th group is called as 7th A and 18th group is designated as 0 group. Here this CAS system, that group number will reflect its maximum valency. That means 7th A group elements maximum valency is 7 or maximum oxidation state is 7. 5th group's maximum is 5. 6th group's maximum valency is 6. That's all. That number is equal to the number of electrons that are possible to involve in the bonding. Now here in 3rd A group we have boron, aluminum, gallium, indium and thallium. And in 4th A we have carbon, silicon, germanium, tin and lead. In 5th A we have nitrogen, phosphorus, arsenic, antimony and bismuth. In 6th A we have oxygen, sulfur, selenium, tellurium and polonium. In 7th year we have fluorine, chlorine, bromine, iodine and actinium. In 0 group we have helium, neon, argon, krypton, xenon and radon. So in all these elements, the differentiating electron will enter in p orbital. That's why they are called as p block elements. Here in the 3rd year group, the electron is p1. Here it is p2. Here it is p3, p4, p5 and here it is p6. Of course, for helium it is only 1s2. This is an exceptional case. This is 2s2, 2p1, 2s2, 2p2, 2s2, 2p3, 2s2, 2p4, 2s2, 2p5, 2s2, 2p6. Here 3s2, here 4s2, 5s2, 6s2 and so on. Almost all nonmetals and metalloids and very few metals are present in this block. Most electronegative elements are present in this area and inert gases are present at extreme end and all non-metals are in this area, metalloids are in this area and metals, very few metals are presented here. All non-metals, all metalloids and very few metals are present in this block. These elements will actively take part into chemical reaction by accepting electrons or by mutual sharing of electrons. That means these elements will involve both covalent bonds and ionic bonds. These elements are said to be p block elements. The general electronic configuration is ns2 np1 to 6. ns2 np1 to 6 is the general electronic configuration of p block elements. P block elements, the elements in which the last electron will enter in p orbital are said to be p block elements. The elements in which last electron, the differentiating electron, will enter in p orbital are said to be p block elements. These p block elements are very reactive elements. Their electronegativities are very high. Except 0 group elements, all other elements will actively take part into chemical reaction by accepting electrons or by mutual sharing of electrons. All nonmetals, metalloids and very few metals are present in this block. Now let us discuss about the 3rd block, that is d block elements. The elements in which the differentiating electron will enter into d orbital are considered as d block elements. Here in the periodic table, from 3rd row to 12th row, are considered as d block elements because in these elements only the last electron will enter in d orbital. The last electron will enter in d orbital. That's why we consider them as d block elements. So in the 4th period, the second element is calcium. Calcium differentiating electron will enter into 4s orbital. After filling up of 4s orbital, now the electron will enter into 3d orbital. So in scandium, the element will enter into 3d, 1. Now after scandium we have titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper and zinc. So here in 10 elements, gradually the d orbital is filled here, d1, here it is d2, here it is d3, here in chromium it is abnormal electronic configuration D5, again D5, then D6, D7, D8, D10, D10. These two are the abnormal chromium and copper. So it's a different thing, we'll discuss in a different context. So this is said to be D block elements. The D block elements properties are quite different from S block and P block elements. S block elements are perfect metals, powerful reducing agents, whereas most of the P block elements are non-metals, and highly electronegative elements are also present there. So the gradual change of metallic character into a non-metal character is reflected by these D block elements. That's why D block elements can also be considered as transitional elements. Transition means change. Transition means change of property. So the gradual change of metallic character into a non-metal character is clearly exhibited by these elements. That's why these elements are said to be transitional elements. And particularly the scandium to zinc, these 10 elements are said to be first transition series. The electronic configuration of these elements is N-1 D 1 to 10 NS 1 to 2. This is the general electronic configuration block elements. D block elements can also be considered as transitional elements because the properties of D block elements are in between the properties of S block and P block. Not only place of this orbital, these D block elements in the periodic table, their properties also are also in the middle of the properties of S block and P block. S block elements are perfect metals, and most of the P block elements are non-metals, metalloids. Only few metals are there. So the gradual change of metallic character into non-metal character can be exhibited by these elements. That's why they are called as transitional elements. Their general electronic configuration is N-1 D 1 to 10, NS 1 to 2 is its general electronic configuration. So other elements, scandium, yttrium, niobium, molybdenum, magnesium, ruthenium, rhenium, Pb, silver, cadmium, then lanthanum, hafnium, tungsten, rhenium, osmium, iridium, platinum, gold, and mercury. We have actinium, this is rutherfordium, so these are said to be D block elements. They are in three complete one series that was in the 7th period. Now let us discuss about the 4th block, that is F block elements. In the 6th period, the 3rd element lanthanum onwards, from cerium to lutetium, nearly 14 elements. Cerium to lutetium, 14 elements. The last electron will enter into F orbital. That means In cesium, 6s2 orbital was already filled. Cesium it is 6s1. After cesium we have barium is 6s2. Then in lanthanum, the electronic configuration is 5d1. After lanthanum, the next electron will enter in 4f orbital. That is in cerium, the electronic configuration is 4f2, 5d0, 6s2. From cerium onwards, in promethium, niobium, samarium, europium, gadolinium, in 14 elements, the last electron will enter into 4f orbital, and these elements are considered as f block elements. These elements are considered as f block elements. Now, the general electronic configuration of f block elements can be considered as n minus 2 f 1 to 14, n minus 1 d 1 to 0, and ns2. This is the general electronic configuration of f block elements. Now, they are cerium, nobelium, Similarly, after actinium in the 7th period, francium, radium and actinium is the third element. After actinium, from thorium to lawrencium. Here also the 14 elements, electron will enter into f orbital. So, these two series are considered as f block elements. Actually, they belongs to 6th and 7th periods, third group of 6th and 7th periods. But it is not possible to display all these elements in one group. Just they were displayed here for convenience sake as a separate row in the periodic table, but they belongs to this 4f series belongs to 6th period and 5f series belongs to 7th period. Most of these elements in the 5f series are artificial elements. Only up to uranium they are naturally occurring elements. After uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelium, nobelium and lawrencium. These are all the, most of them are countries' names, scientist names and planet names and some universities names, because here you have plutonium is a planet, neptunium is also a planet, americium is an American country. So, this is curium, Madame Curie, berkelium, it's conducted in Berkelium University, and californium, California City, einsteinium, Einstein, fermium, Fermi, mendelium, Mendeleev, the father of this periodic table, and nobelium, Albert Nobel, lawrencium, a Russian scientist. So, on the name of those scientists, these names were given to these elements, and most of the elements after uranium, almost all elements in after uranium are artificial elements, and they are considered as F block elements. Now, classification of elements into 4 types basing on their properties. The elements that were present in the periodic table can also be classified basing on their properties. Previously, we have classified the elements into 4 blocks depending upon the orbital in which the last electron is entering. But here, this is more scientific classification. which depends upon properties of elements, particularly mainly properties of elements, irrespective of the orbital in which the electron is entering. Here we are going to classify the elements into 4 types basing on their properties. They are inert gases, representative elements, transitional elements, and inert transitional elements. Now, in present class, we are discussing about the classification of elements basing on their properties. Basing on the properties, the elements of the periodic table can be classified into 4 types. They are inert gases, representative elements, transitional elements, and inert transitional elements. Now, let us discuss these elements one by one. The first type is inert gases. Inert means reluctant to take part into a chemical reaction or a chemical bond. There are certain gases which are reluctant to take part into the chemical reactions. The main reason for their inertness is their valence shell is having a maximum number of electrons. That is, the maximum number of electrons that can present in any valence shell is 8. So, in these inert gases, the valence shell is consisting of 8 electrons. That means in all these elements, including valence shell, all inner shells are completely filled. The elements which are present in the, are represented in the 18th vertical column of the periodic table is considered as inert gases or zero group elements. This is 18th group or zero group. Here we have helium, neon, argon, krypton, xenon, and radon. Of course, radon is a radioactive element, and all the remaining elements except radon, helium, neon, argon, krypton, xenon, and radon, they are present in air along with oxygen and nitrogen. In normal cases, they won't take part into chemical reactions. That's why they are called as inert gases. But it was found that in extraordinary conditions, xenon and krypton are found to form certain compounds with oxygen and fluorine. Now, the name inert gases is replaced, and these elements are presently calling as noble gases. They are in gaseous state, and that's why we call it as noble gases. Except helium, in all these elements, the valence electronic configuration is ns2 np6. The general electronic configuration of these elements is ns2 np6. This is 8 electrons in their valency shell, where for helium it is 1s, first energy level, cannot accommodate more than 2 electrons. So, all these elements, since they are obtaining in air, present in air, they are also called as aerogens. Inert gases are also called as aerogens. Inert gases, the elements which are present in the 18th vertical column of the periodic table, are considered as zero group elements or 18th group elements. These elements are reluctant to take part into chemical reactions at normal conditions. That's why they are called as inert gases. Since these gases are present in air along with oxygen and nitrogen, they are considered as aerogens. They are considered as aerogens. The general electronic configuration of these elements is ns2 np6. The general electronic configuration of these elements is ns2 np6. But in extraordinary conditions, krypton and xenon are found to form certain compounds with highly reactive elements like fluorine and oxygen. That's why now the name inert gases is not considering for these elements, and now they are calling as noble gases. Now, the second type of elements is representative elements. Except these inert gases, the total S block and P block elements and P block elements elements. In this universe, the elements are present in the form of different compounds. Whatever the compound that you have taken, definitely one of these element is present in it. This type of, that is from first year to seventh year group elements, at least one element is present in any one of the compound. That's why, since they are present in each and every compound, they are considered as representative elements. And there is other reason also. These elements will exhibit the properties well excellently that was present below them in the period given certain group. For example, that means here if you take magnesium, magnesium will reflect the properties of calcium, strontium and barium. Similarly, sodium will reflect the properties of potassium, sodium, that we call as representing nature. So these are the two reasons for claiming these elements as representative elements. The general electronic configuration of these elements is NS2 NS1 2 NS2 NP5 NS1 2 NS2 NP5. All configurations are there. Or we can say NS122 NP12. Only valency shell is incompletely filled, whereas all inner shells are completely filled. In inert gases, including valency shell, all energy levels are completely filled with electrons. Whereas in representative elements, only valency shell is incompletely filled. Because of this, to get stability, these representative elements will actively take part into all types of chemical reactions. That means they involve in ionic bond formation as well as covalent bond formation. Representative elements. Except inert gases, all the remaining S and P block elements are considered as representative elements. In these elements, valency shell is incompletely filled, and these elements are actively take part into chemical reactions by donating or accepting of electrons or by mutual sharing of electrons. They actively take part into chemical reactions and form different compounds. These elements are present as one of the constituent, or at least one element will present in any compound that was present in this universe. That's why these elements are said to be called as representative elements. They are very active elements, actively take part into chemical reactions. Only valency shell is incompletely filled. Next, third type of elements is transitional elements. The D block elements are considered as transitional elements. The third row to 12th row. The name transition means change. These elements are present at the middle of the periodic table, in between S block and P block. Not only their position, their properties are also intermediate or middle between the properties of S block elements and P block elements. S block elements are perfect metals, P block elements are non-metals, metalloids. So the gradual change of metallic character into non-metal character is clearly observed by these elements. That's why these elements are said to be transitional elements. In these elements, last two energy levels are incompletely filled. Remember, in inert gases, inert gases, almost all orbitals, including valency shell, is completely filled with electrons. In representative elements, only valency shell is incompletely filled. In transitional elements, valency shell and penultimate shell, n shell and n minus 1 shell will also be incompletely filled with electrons. Last two energy levels are incompletely filled. Representative elements, only last energy level is incompletely filled, whereas inert gases, including valency shell, all energy levels are completely filled with electrons. Because of the availability of empty orbitals in the valency shell, the transition elements will exhibit different colors because of the presence of this d electron. First one is the transitional elements will form colored compounds. Transition elements will form colored compound because this d orbital, which will have 5 d, can be degenerated into two ways. 3 electrons, that means 3 orbitals which are along in between the axis, and other 2 orbitals which are along axis. And this 5 orbitals is again degenerated, so that due to the transition of electrons within these energy levels, they absorb certain wavelengths of this visible light radiations, then they exhibit in different colors. Potassium dichromate, because of chromium, it is an orange in color. Potassium chromate, yellow in color. Potassium permanganate, violet in color. And almost all these elements of d block elements, they form colored compounds because of the d electrons, transition of d electrons within the d orbital. And they are, most of the d orbital, d block elements are paramagnetic in nature. And these elements, in addition to ionic bond and covalent bond, these elements can form additionally covalent coordinate bond. That's why they are able to form complex compounds. They form colored compounds, they show paramagnetic nature, and they form complex compounds or coordinate compounds. And here another important characteristic property is formation of alloys. The atomic size of transitional elements is almost equal. Since they have size is much less difference in between one atom to other atom, their crystal structures are same. Because of the similar crystal structures, the transition elements are easily forms alloys. Alloys means a homogeneous mixture of two or more elements with a metallic character is said to be alloy. D block elements can easily form alloys. So, the characteristic properties of D block elements are, number 1, they form colored compounds, they are paramagnetic in nature, they form complex compounds, and they can form easily forms alloys. So, these are the important characteristic properties of these transitional elements. The general electronic configuration of these elements is n-1, D, 1 to 10, and ns2. And these elements will show variable oxidation states by losing of ns electrons as well as n-1d electrons. They exhibit different types of oxidation states and form stable compounds with different oxidation states. These are the important characteristic properties of these transitional elements. Now, F block as inert transition in the properties of transitional elements. That's why they are called as inert transitional elements. They are in two series, 4F series and 5F series. 4F series are said to be lanthanides and 5F series is said to be actinides. Their existence in this universe is very few, less, because the less quantity they are present in this earth. And in 4F series and 5F series, most of the elements are artificial elements. So, F block elements are considered as inert transitional elements. In F block, last 3 energy levels are incompletely filled. Valency shell, n-1 shell and n-2 shell is incompletely filled. Remember, in inert gases, including valency shell, all energy levels are completely filled. In representative elements, only valency shell is incompletely filled. In transition elements, last two energy levels are incompletely filled, whereas in inner transitional elements, last three energy levels are incompletely filled. So, we will discuss the properties of these elements in detail in next class.